The next class of differential equations that we'll define are autonomous differential equations. An autonomous differential equation is a differential equation of the form dy dt equals f of y. That is, a differential equation where dy dt can be written just in terms of y and not in t. We've seen examples of autonomous differential equations in the compound interest and modeling of the mouse populations. And for our next example of an autonomous differential equation, let's revisit that population model and improve on it. Our most basic population model says that the rate of change of a population is proportional to the population. That is, dy dt is equal to r times y, where y is the population and r is a constant called the growth rate. As we can see, this is an example of an autonomous differential equation. And for a starting population y of 0 equals y naught, we can obtain the solution y equals y naught times e to the rt. If you'd like to do this on your own, you'd want to divide by y on both sides and integrate as a separable differential equation. This model isn't perfect though. The problem with this model is that the long-run behavior of y is to tend towards infinity, which doesn't make sense in a real-world application of populations. Natural environments can only sustain so large of a population. We call this maximum population that an environment can sustain the carrying capacity. So how can we modify our population model so that dy dt behaves like r times y, our original growth model, when y is small, and decreases as y approaches the carrying capacity k, so that it doesn't go over the maximum? The easiest change to our current model is to multiply by the factor 1 minus y over k. That way, for small values of y over k is roughly 0, and thus 1 minus y over k is roughly 1. So we're multiplying by a factor close to 1, not changing it very much. And as y goes to k, y over k is roughly 1, and thus 1 minus y over k is roughly 0, meaning that our rate of change for the population, dy dt, also is tending towards 0. This gives our new population model called the logistic growth model, which is dy dt equals r times our new factor, 1 minus y over k, times y. For our logistic growth model, with growth rate r and carrying capacity k, let's analyze it by looking at its equilibrium solutions as we have in the past. Remember, the equilibrium solutions happen when dy dt equals 0 for all values of t, which for this differential equation is r times 1 minus y over k times y equals 0. Since this is already factored, we can see that the equilibrium solutions happen when either 1 minus y over k is 0 or y equals 0. Since if we multiply several numbers together and get 0, one of them must be 0, and the growth rate r is greater than 0. And the growth rate r must be greater than 0, otherwise there wouldn't be population growth. So one of the equilibrium solutions happens at y equals 0, and solving the first equation, we get that y equals k. So we can conclude that the equilibrium solutions happen at y equals 0 and at y equals k. So what information can we get about our differential equation and our function y from these equilibrium solutions? The equilibrium solutions tell us that if the population is 0 or the population is k, then the growth will be 0 and the population model will stay stagnant. This makes sense. If there's 0 population of something, that population will stay at 0. And if the population is at the maximum, the carrying capacity k, then the population will also stay at that maximum. But what can we conclude about other solutions? Let's think about values of y that land between 0 and k or bigger than k. If y is greater than k, then dy dt is equal to r times 1 minus y over k times y, where r is some positive number. Y minus k will be a negative number, since y will be bigger than k, and thus k over k will be bigger than 1, and y itself is also a positive number, since the maximum k must be bigger than 0. So we have dy dt is equal to a positive number times a negative number times another positive number, which must be negative itself. So we can conclude that for values of y bigger than k above the carrying capacity, y is decreasing. This makes sense because if the population is higher than the maximum sustainable amount, then the population will decrease down to that maximum k. And we can do a similar analysis for y between 0 and k and y less than 0. Although in this application of a population model, y less than 0 doesn't really make sense. But we can do it for the theoretical purposes that may come up in other scenarios anyways. In the case where y is between 0 and k, we still have dy dt equal to r times 1 minus y over k times y, where r is still positive, but now because y is less than k, y over k is less than 1, and 1 minus y over k is bigger than 0, is positive. And since y is bigger than 0, y itself is positive, so dy dt is 3 positive numbers multiplied together, which again gives us a positive number. So since dy dt is positive, we can conclude that for y between 0 and k, y is increasing. Lastly, if y is negative, then dy dt is going to be a positive number, r, times another positive number. Since y is less than 0, it must be less than k, and again 1 minus y over k will be positive. But then we have times y, which itself is a negative number. So dy dt is negative, meaning that for y less than 0, y is decreasing, which again, in a population model, doesn't quite make sense, but it could be applicable in other real-life scenarios. A helpful tool to consolidate all this information is a phase line. With a phase line, we keep track of which values of y lead to a positive derivative and thus y increasing, and which values of y lead to a negative derivative and thus y is decreasing. The arrows on the phase line indicate whether y is increasing or decreasing. The phase line for this differential equation will have values of y that are bigger than k with a negative derivative, and thus the arrow will point down towards k. For values of y between 0 and k, the derivative is positive, and thus the arrow on our phase line points up towards k. And lastly, for values of y less than 0, the derivative is negative, and the values of y decrease down away from 0. Note that this is most helpful when we have autonomous differential equations, because all the information we need to calculate the derivative is y. We don't need to know the t value, so we don't need to look at the entire phase plane. However, the functions y that are solutions to the differential equation are functions of t. So it's still useful to look at the yt plane and sketch what our solutions will look like. The information that we get from this phase line will dictate what those solutions look like, though. If we look at the integral curves, which are the solution curves, with the phase line, we can draw these conclusions about our equilibrium solutions. Notice here that we have equilibrium solutions at y equals 0 and y equals k, indicated by those horizontal red lines. For solutions where y naught is bigger than k, those solutions will decrease down towards the maximum k, while solutions where y naught is less than k will have solutions that tend up towards the carrying capacity k. Since solutions that start near the equilibrium solutions, y equal k, tend towards this equilibrium solution, we call it an asymptotically stable solution, because any solution that starts nearby k will either tend up or tend down towards that solution k. On the other hand, since solutions that start near the equilibrium solution y equals 0 diverge away from this equilibrium solution, we call it an unstable solution. in terms of our population model, the way that we can think of this is if the population is slightly bigger than 0, but is not 0, the population will grow up to that maximum sustainable amount. But even this model is not perfect, because if you say introduced one mouse into a field, that one mouse wouldn't be able to reproduce and have the population grow up to the carrying capacity. So even this model can be improved upon. Further models include a threshold amount, that if the population is below the threshold, it will decrease down to 0, so that you have to have a minimum amount in order to grow up to that maximum amount.